Before we explore the tangent on the unit circle and how to visualize it, we first need to understand what tangent actually is. We'll see, for example, how it can be used to calculate the height of a tree, and also discover its connection to the steep grade signs you see on mountain roads. Someone might ask, why invent a new term called tangent when we can simply take sine divided by cosine? The short answer? Efficiency and real-world practicality. Technically, yes, tangent is nothing more than the sine of theta divided by the cosine of theta. So at first it might seem unnecessary. But in reality, tangent exists because it solves a very concrete problem that sine and cosine cannot solve directly: the absence of the hypotenuse. That's the real issue. Both sine and cosine require the hypotenuse. But in real life, in architecture, surveying, or even astronomy, the hypotenuse is often the hardest length to obtain. To truly understand why tangent exists, let's look at a few concrete examples. Let's start with something very simple: measuring the height of a tree. Imagine we want to measure the height of this tree. For a moment, let's forget about tangent and try to solve the problem another way. Here is the information we have: the horizontal ground distance, which is easy to measure, the angle theta, which can be measured with an instrument, but not the hypotenuse, which remains difficult to measure accurately through the air. Let's try to find the height anyway. First method, the Pythagorean theorem. In our right triangle, we know that the hypotenuse squared is equal to the ground distance squared plus the height squared. If we isolate the height, we get the height squared equals the hypotenuse squared minus the ground distance squared. Problem: we are completely stuck because we don't know the hypotenuse. The calculation stops there. Second method, using sine or cosine. The sine of theta is the opposite side divided by the hypotenuse. More concretely, it's the height divided by the hypotenuse. So the height would be equal to the sine of theta multiplied by the hypotenuse. Once again, this is impossible to calculate because the hypotenuse is unknown. And what about cosine? It gives us the adjacent side divided by the hypotenuse, or simply the ground distance divided by the hypotenuse. That doesn't help us at all in finding the height. And this is where tangent comes in to save us. Tangent doesn't require the hypotenuse. It directly relates the opposite side to the adjacent side. In other words, it directly relates the height to the horizontal ground distance. So, the tangent of theta equals the height divided by the ground distance. Therefore, if we isolate what we are looking for, the height equals the ground distance multiplied by the tangent of theta. And now all the data is known. There is no need to measure the hypotenuse. The problem immediately becomes solvable. Tangent wasn't invented just for the sake of elegance. It exists because it directly connects a vertical height to a horizontal distance, without ever going through the hypotenuse. And that is exactly what we need in the real world. We've just seen that tangent can be used to calculate an inaccessible height, like the height of our tree. But did you know that it also plays a role every day beneath our tires, helping to keep our roads safe? You've probably already seen this kind of sign on the highway or in the mountains. It indicates a steep downhill slope. Here, for example, 10%. But be careful, what does that 10% actually mean? Many people think it means an angle of 10 degrees. That's false. In civil engineering, it simply means that for every 100 meters traveled horizontally, the road drops by 10 meters vertically. If we draw these two lengths, we end up once again with our familiar figure, the right triangle. Let's apply our logic. Our horizontal distance of 100 meters is the adjacent side, and our drop of 10 meters is the opposite side. We'll call this angle right here theta. This is where the magic happens. Remember the tangent formula? The opposite side divided by the adjacent side. Here, that gives us 10 divided by 100, which equals 0.10. And 0.10 expressed as a percentage is exactly 10%. So the number written on the sign is nothing more than the tangent of the road's angle. Tangent isn't just a button on your calculator. It's a direct measure of slope used by engineers to help keep you safe on the road. So far, we've seen tangent through right triangles, whether to calculate an inaccessible height or to understand the slope of a road. But now, let's leave the physical world behind, dive into pure geometry, and see how tangent is represented on the unit circle. To read the tangent of an angle properly, we first need to construct a very special line. Look at the rightmost edge of the circle. We're going to draw a vertical line there, just touching it. Notice something important. This line doesn't pass through the circle, and it doesn't cut it in half. It touches it at one single point, and one point only. That's precisely why it's called the tangent line. In our coordinate plane, this perfect point of contact corresponds to the coordinates 1, 0. Now, let's place a point on our unit circle. To begin, let's position it at pi over 4. This point forms the angle theta with the horizontal axis. To read the tangent of theta, all we have to do is take the side of the angle and extend it directly until it meets the tangent line. The length of this red vertical segment, measured from the x-axis, is exactly the value of the tangent. Here, at pi over 4, we can see geometrically that it's exactly 1. Now, let's decrease the angle until it reaches 0. The side of the angle becomes perfectly horizontal. The intersection height becomes 0, and so the tangent of 0 is simply 0. Now, let's increase the angle and stop at a special angle, pi over 6. Here, the tangent is exactly the square root of 3 divided by 3, which corresponds to about 0.58 on our axis. Let's continue the rotation. Watch carefully what happens as we approach pi over 2. The side of the angle becomes steeper and steeper, and the value of the tangent shoots up very quickly toward infinity. At the exact moment we reach pi over 2, the side of the angle becomes strictly parallel to our tangent line. Since they're parallel, they'll never meet. That's the geometric reason why the tangent of pi over 2 is undefined. Let's keep going. As we move into the second quadrant, for example here with an angle of 5 pi over 7, the extended side of the angle hits the tangent line below the x-axis. So the value we read is negative. As we continue to pi and complete a half turn, we return to a horizontal line, and the tangent becomes exactly 0. In the third quadrant, let's take the angle 8 pi over 7. The extended side of the angle hits the tangent line above the x-axis once again, so the tangent becomes positive again. The closer we get to 3 pi over 2, the more the intersection shoots off toward positive infinity. And naturally, at exactly 3 pi over 2, the side of the angle is completely vertical. The lines are once again parallel, so the tangent is undefined there as well, just as it was at pi over 2. Finally, in the last quadrant, for example with an angle of 9 pi over 5, the extended side of the angle points downward once again, giving a negative tangent. This value then gradually rises back up to 0, completing our full turn at 2 pi. Now that we have a clear picture of tangent on the unit circle, an essential question arises. Why is the tangent of an angle equal to its sine divided by its cosine? In class, you're often given this formula as just a rule to memorize. But here, we're going to see that it follows directly from geometry. Let's return to our unit circle. We have a point M on the circle that forms the angle theta. If we project this point M onto the horizontal axis, we get the value of our cosine. And if we project it onto the vertical axis, we get the value of our sine. Now, let's bring back our tangent line and extend the side of the angle exactly as we did earlier. This vertical segment measured on the tangent line represents exactly the tangent of theta. Now, let's reposition the sine segment so that it forms a right triangle. Look at the figure as a whole. We actually have two right triangles nested inside each other, sharing exactly the same angle, theta. This is the perfect situation for applying the properties of similar triangles. Geometry tells us that in such a configuration, the corresponding sides of these two triangles are proportional. Let's take the smaller triangle. If we divide its height, which corresponds to the sine, by its base, which corresponds to the cosine, we get sine of theta over cosine of theta. Because the triangles are similar, this ratio is equal to the corresponding ratio in the larger triangle. In this larger triangle, the height is the tangent and the base is simply the radius of the circle, which is equal to 1. So in the end, we get sine of theta over cosine of theta is equal to tangent of theta over 1. Therefore, tangent of theta is equal to sine of theta over cosine of theta.